my slide up so you can see the slide, or my demo's up, I won't be able to see the hands. So how? Oh, I know what to do. If somebody has a question, you can ask. Raise your hand. Katrine will see your hand and unmute, and then I get my attention that way. But anyway, what I want to what I wanted to talk about tonight was property-based testing. How many people here have used ScalaCheck before? About a third, yes. I see you over there. Okay, that's good. So what essentially the talk is about is we have added a generator to ScalaTest. We're in the process of finishing that. So it's actually a work in progress, which makes the demos more exciting. And it's, I'm going to ask your opinion on a couple of things, or anything you actually have as a suggestion or a criticism of the way, some decisions we've made. I would like to hear it because there's still time to change things. So you may have some influence in what we end up doing. But I wanted to start with, so I'll go over here, and I wonder if I can actually just, yeah, this should work. You can see that if I do that. No, wait, I didn't share my screen. Let me go back and share my screen. Share my screen. That would be this guy. And you can see yourselves. That's what you look like. This is what my slide looks like. And that should work. If it doesn't work, you can unmute and let me know. But essentially, what I am showing here is a code, a function written in a language that isn't Scala. Can anybody, let's go back and look at you guys. Can anybody tell me what language that is? Anybody know this language? I hear silence. Of course, you're on mute. You're probably all yelling, Eiffel.
No, not on mute anymore.
Okay. Yeah, that's Eiffel.
That's Eiffel.
And it's a language written by a guy named Bertrand Meyer. He's French. And so he named it after the Eiffel Tower. It was maybe in the 80s or something. This was competing with C++ for mind share, and it lost pretty much to C++. But one of the ideas that he had in his language and in his big, huge book about object-oriented programming, which became kind of a classic, is he called design by contract. And what design by contract had was when you basically this notion of preconditions and postconditions, which he expressed as assertions. And when you wrote a function body, you didn't just write the implementation of the function. You wrote, there were 3 sections to it. There's a require section where you express the preconditions of the function. So this is a square root function. It's going to take a real number. And you can only take the square root of a positive real number, or 0, right? So his require clause says x has to be greater than or equal to 0. So that pass value has to be greater than or equal to 0. And then then you have the do. That was actually where you express the body. Those 3 little dots there is the body, or that's like the normal part of the function. And then at the end, you have an ensure clause, which was the post condition. So here, what he did for the post condition is squared the result. So capital R result is just magic variable inside an ensure clause, which is what you're about to return. So he squares that, and if you take the square root of something and then square it, you should, in the ideal world, get back the original. But because of rounding, it might be slightly different. So what he does is he subtracts the original, and that should be in the ideal world 0. But it might be a really tiny, small difference. And so you take the absolute value of that to make sure it's positive. And then you just check it against a tolerance. So that's sort of the idea. And then we'll go back to look at you guys. So the wait a minute, let me do this. There. So the idea was that preconditions are a responsibility of the caller. The person who calls the square root function has to make sure he doesn't ever pass in a negative double or real in that case. And the ensure clause, the post condition, was the responsibility of the person who's implementing that do, right? Who's actually providing the service and actually computing the square root. So that was like this notion of who's responsible for what. And what when there is a way to do this style in Scala, which is not that well known. I'm curious how many people know about this. So here's Here's what that looks like in Scala right here. I've got a square root function, and it takes a double and returns a double. And then I have this thing called assume that is like assert. It just throws assertion error, but it's intended for precondition checks. And just like in Eiffel, you can, one of the ideas of assertions, which also made it into Java, is you can elide them at runtime. And his idea way back in the 80s was that, this could be expensive, especially computing post conditions might be expensive, but even preconditions might be expensive. And so it's something you want to do for sure during testing and development probably, but you might want to turn some of them off at runtime. And so, this is assume is like assert can be turned off at runtime in Scala. And the way Scala does it is with something called an elide level. So there's just a general way to elide code at runtime based on a level, which is just an int. So then we have math square root x. So what this does, what math square root x does if you pass in a negative number is it gives you back not a number. So what this square root function that we're writing here does differently is if you pass in a negative number, it throws an assertion error. And then you can call ensuring. So I'm gonna actually demo that in my demos, and I think I'll do is probably make this larger so you can see it there. Okay, so if I say like 42, that's 42, I can say dot ensuring, and then I kind of pass in a function that takes this value you call it on. So I coming in is going to be 42, and I could say I is greater than 0. And what this does is this is an assertion. You're doing an assertion at the end. You're doing an assertion on this value, right? And that passed the assertion, so the result of ensuring is just what it was invoked on. But if it fails, then it'll give you an assertion error. So that's something that you can do in Scala and could have for like the last 10 years, but you rarely see that used. And it is for this design by contract style. And this can also be elided. If you turn off assertions, then what it does is it does actually invoke this method, but it never invokes this function. So it's a little bit, it's not as nice as Eiffel, where you just wouldn't have any execution at all. So anyway, that's I think what it didn't actually survive in the it didn't win in the marketplace of ideas really doing this design by contract stuff, even though it seems like a good idea. What won in the marketplace of ideas, first of all, Eiffel didn't win, C++ did, and then along came Java, and then along came JUnit. So what actually what we do, even in the Scala community and the JVM, on the Java community, is we do express preconditions, but in a way that you can't turn them off. So instead of it being an assertion, you use require, which throws a legal argument exception, and this cannot be elided. It is always checked. And the reason for that, that is actually the default for Eiffel, is that preconditions are turned on and postconditions are turned off. So then we implement the body, we sort of do the do part, and then we don't ever do an ensuring usually. And what we do instead is we put that in a test. Right, so here's this separate thing called test, and this guy named Kent Beck and Eric Gum. Eric Gum wrote the Gang of Four Design Patterns book, which was influential. And Kent Beck was just a famous consultant, wrote a bunch of books. And they together whipped up this thing called JUnit, and that's actually what won in the marketplace. Is you put these little precondition checks in a way that you can't turn them off, which was the default in Eiffel, and you put the ensuring, the post-condition checks, is actually over in a test. So what I did is, in this test, I used a property-based test in ScalaTest syntax, which is you say for all. And this is like the logical for all doubles is what this means. Whenever the precondition is true, which, if you remember, the precondition was a require clause now, and it said x has to be greater than or equal to 0, and it can't be positive infinity, because that also gives you not a number, I guess. I compute the square root, and now I've called that result. I compute a tolerance, and then I just do the same formula. I square the result. That should be 0 in the ideal world, and then I use plus or minus. I don't have to absolute value it. That's fine also. So that's basically the way that works in that's sort of what won in the marketplace. So what I think is that this way of expressing it is like a statement of logic, and that is really the essence of what a test is. That a test is a statement of logic in this format. So for example, this is how you would write it in predicate logic. This little upside down A means for all, so for all x's. In our case, it's of type double. P of x is like P and Q are predicate functions. So you pass in x into the predicate function, it'll return true or false. So in this case, the predicate function is a function that takes an x and says x is greater than or equal to 0, and it's not positive infinity, right? That true or false. So that's the first thing. If that is true, that implies that the post condition is true, and the post condition is I'm testing f, so I compute the result f of x, and then I have a predicate on like the result, and also I have x available too. So over here, my predicate, of course, is that this guy right here. That the squaring the result should be the original plus or minus a tolerance. Okay, I'm going to stop right there and go back and see if anybody has any questions. I'll stop periodically to see if you guys have questions, since it's hard for you to interrupt me. So any comments so far?
Doesn't look like.
All makes sense? You buy all that? Everybody is completely believing everything I say so far. Okay, great. I will carry on. If you can mute me. It's amazing how distracting it is to hear your own echo. Anyway, so what we're doing in ScalaTest 3.1, excuse me, is we're migrating all third-party integrations to modules. So first of all, ScalaTest is really big, and so it'd be nice to make it smaller. And one way to make it smaller is there's a package for JUnit that's just useful for people who use JUnit. There's a package for Mockito, which is useful for people who use Mockito. There's one for EasyMock. There's one for JMock. There's one for ScalaCheck. There's one for TestNG. There's one for Selenium. And all that is like in this big, massive library. So what we want to do is take all these things that are third parties and move them separate. So we're going to rename the packages for the ScalaCheck integration and all the other ones so that we can have them be separate modules. And what that means is basically, if you just grab ScalaTest, you'll get everything. But you can just grab pieces, and you won't get, just have like smaller pieces that are just the things you're using and just the things you want people in your project to use, right? So they'll have fewer choices unless they want to go change the build and bring in more stuff. So we're also adding a generator in to ScalaTest in 3.1, which one of the reasons is that ScalaTest is early in the well, there's this sort of chain of builds when the new version of Scala comes out. ScalaTest is at the very early part of that chain because a lot of projects use ScalaTest, and ScalaTest depends on Scala XML and ScalaCheck. So ScalaCheck, it sometimes takes a while to get to work. So like from August 3rd to October 9th, we were waiting on ScalaCheck for 2.13.0 M5, for example, and that's because that was the milestone release of 2.13 where they broke collections. But essentially, we want to remove that dependency and move it out to be, we don't have to wait for them. So so we'll do our own property-based testing with our own generator internally. And we also, there's a bunch of things that we wanted to try different ways. So that's the kind of things I wanted to get feedback from you guys on. And so I mean, there's a long list here. I'll go through these things tonight, but there are many differences that we'd like to try to make improvements that were hard to do in ScalaCheck. And so one of them is generators are variable directly. I'll just show you some demos here. Whoops. I go here. So I have a little project that's depending on basically this is a project that's depending on a local build that I just made of ScalaTest that 3.1.x branch. So some of the stuff you're going to see here isn't actually out in the wild yet.
Bill, yeah. I don't know if you remember to share.
Oh no, I did not.
Okay.
All right. I just wondered when you came on. I wondered about that. Okay, so let's go down here. Okay. All right. So what essentially you can do? I'm going to just grab it from here. Yeah. So here's one difference. This is a very minor thing, but it's kind of we never quite understood why. In ScalaCheck, you have to grab your generator out of arbitrary. An arbitrary, I think you say arbitrary, right? Yeah. So basically what's available implicitly is a wrapper for a generator of events. And then I can, so that this is this SCArb has type arbitrary event. And inside of that, if you call its arbitrary method, you get a gen event. And so with the gen event, I can get a sample, for example. And I can, so it'll just give me different ends, right? And so that's what a generator does, is it generates. And then in ScalaTest, you just actually, we just make the generators implicit. So that's what's actually being passed in. There's no extra wrapper there. And so that's one small difference. We got rid of the arbitrary wrapper. And so another thing is that essentially what these guys are for is for generating things. So and you can compose new generators out of old generators. So one of the other things that's different than ScalaCheck is ScalaCheck would generate option of t's. So you may notice it is that ScalaCheck didn't just generate an int; it generated some int over and over and over, right? Whereas ScalaTest generator just generates an int. So one of the ways that you can compose a new generator out of an old one in ScalaCheck is called such that. And what I'm going to do is I'm going to take the int gen that we made up above, ScalaCheck int gen, and then I'll call such that on it, and I'll pass in a function that is only true if I is positive. So now here's my ScalaCheck positive int generator. And so if I say pos int gen, what you'll sample, you'll start seeing some nuns. So that basically what happened is those came out negative, and so he filtered them out, right? Wow, that's a lot of nuns. Should be about half nuns over time. So, so that what you can't do. There's no such method like such that in ScalaTest. What you'll have to do is what you can do with ScalaCheck also is use a for expression. So the normal way to compose a new generator out of an old generator, whether using ScalaCheck or ScalaTest's generator, is to say, like, for I in st int gen, what's it called? St int gen? Is that a thing? Yes. And then I'm going to say j is equal to, what do I want to do? Get rid of 0 and greater. Yeah, if I is less than or equal to 0, that's what I want to get rid of. Then I'm going to say I don't want to do that with 0. Let's see. I want to get rid of anything. Well, let's see. Well, you know what I'm going to do? I'm going to always use 42. That's a terrible thing. I'll say, let's do this. If I equals 0, 42, else if, I don't know if this will actually parse, I is less than 0, because I want to get rid of that. I'll just say I.abs. I. See if that works. And there's a bug there. I'll see if anybody can spot it. I'll yield j. So that did actually compile. So what I will get, basically, if the old int gen generates a negative number, if it generates a 0, I'm going to get 42. If it generates a negative number, that's negative, then I'll get I'll just make it positive. So if I say pos int gen dot sample, I just get positive numbers, and then ScalaTest you can say samples 100 and see a bunch of them. So they're all positive numbers. So does anybody see a bug in here? Is there any way this could go wrong? And it's actually in this part. Anybody see?
Unmuted, waiting for results.
If it's the minimum integer number, there is no representation.
Yeah. Int.min value val x equals. So that one, if you look at val y equals int.max value, it's one less, right? That's how 2's complement works. So if I say x.abs, you get a negative number. So there's still some way. That's like a bug in this generator here. I would need to actually pull out int.min value also, like I did 0 here, and give it a special number if I wanted that to be correct. But anyway, okay. So that's kind of two kind of minor differences, I think, between ScalaTest and ScalaCheck. Okay, so the other demo, I'd like to show you randomizer. So one of the things that was important is to be able to, if I can find IntelliJ, where's IntelliJ? That's it. To be able to reproduce tests. So there's this flaky test spec here. It's very small for you probably. And what it has one test in it called incrementing an int, and it says for all ints x named x plus 1 should be greater than x. So there's one place where that's a bug. Can anybody tell me how this can blow up?
Say max value.
Yeah, max value. So let's try it. I can say let me get out of here. Quit. Test only star. Actually, let me do this. Hide. Test only star flaky. Test spec. Let's see if that works. Okay, so that did work. So I got a flaky test, but it should. I mean, it failed, but it should sometimes succeed if I can get it to succeed. There, that succeeded that time, right? It depends on whether or not it tries max int, and max int's an edge condition which we favor, so it does actually fail more than 1 out of 2 to the 32 times. But what you can do is there's this seed printed out here, and if you say provide it when you run a test, then it'll always use that same seed for the random number generator, and it becomes repeatable. Right, so that was something that ScalaCheck couldn't do before because they used a mutable random number generator, just Java's random number generator. Since we did this, this actually has been fixed in ScalaCheck. It's also reproducible now. But what it requires is that the random number generator has to be functional, which is kind of sounds weird, but what that looks like, I'm going to exit out of this and say, oh, by the way, let me actually do one other thing, because I didn't fix it. And the nice thing is, like, when you go to fix it, you'll know that you're testing the same thing. So one way to fix this would be to put a precondition check whenever x does not equal int.max value. And LJ is going to put the closing place wrong there. So, boy, you can't see because it's popping up all this information, but all I did was I added this. So this is a precondition check. It says for all x's, for all ints, I mean, whenever int is not equal int.max value, this property should hold true. And so now I'm testing it with the exact same thing. So when it goes green, I know that I fixed my bug. There we go. So that's consistent. Okay, so let me exit out of here. And oops, didn't mean to exit out of here. I'm going to go back into the REPL. Okay. So yeah, so randomizer is what I wanted to show you. And what randomizer has on it, I have one called R&D, which is like the default randomizer. I'll call it val R equals R&D. Let's see. R&D is going to actually equals R&D. This guy is going to call randomizer.default, which each time you call it will give you a different seed, essentially. But now that I've created this one R, it's always going to have the same seed. So if I ask it for the next int, it'll give me some number, right? If I ask it for the next int again, it'll give me the exact same number because it's an immutable class. It just remembers this immutable seed and it does the same thing each time. But it doesn't just give me back an int, though. It also gives me back the next randomizer. So you have to feed the randomizer through. Like when you're generating values and you're using this random number generator, you always pass it through. So what I would do is I would say val, j, comma, next r, next random, next R&D, something like that, equals. So now I've got another one here. and I would use that to get my next int, for example. Now it's a different number. So so that's randomizer, and I think I'll go ahead and stop here and see if there's any questions for that. How do I stop sharing? Anybody have a question? I can find.
Yes, there is a question.
So I'm just wondering, when you have whenever condition, how would you choose the values within this predicate? So what if I say for all double, but I'm only interested in like very small interval, from 0 to 001. So is it going to basically try millions of numbers before it will find the number?
Yeah. So that's a good question. If you can mute, I'll try to. Yeah, sorry, I can't figure out how to stop my screen sharing. I don't know, I want to hang up on you, so I'll just show you your cells for a second. But to make sure I understood the question is, using a whenever clause, let's say I have, my whenever clause is, these are all ints. What if I only wanted 0, 1, and 2? I could say whenever x is equals 0 or x equals 1. And now it's going to generate 2 to the 32 different possible ints, and I'm only using 2 of them. Is that your question? Like,
okay. The answer was yes.
Yeah,
okay.
For other types, like for integer, it's reasonable. But for some other types, it can be like almost infinite possibilities. How is it going to find the one that you have restricted?
Can you repeat that closer to the mic?
Sure. So it's maybe if you, or I can, okay, so it's going to be my interpretation. So if it's doubles, it means that if the answer is that it's going over, like it's only throwing out the numbers that it does need, it might be infinite time to get to enough numbers that you want to choose for the certain.
Okay, let's try it. What happens is that I don't need this anymore. It doesn't matter. It will actually cause a test failure, and you give up after a while. Let's say too many things have been discarded. It'll tell you giving up after one. Oh, he actually got one successful property. 49 evaluations were discarded. So we have a max discarded config parameter that if it like tries, I don't know why it's 49. I would think it would be 50, but it's kind of odd. I don't know why that says 4. See, this is a work in progress, so I'm going to actually check why that's 49. I should actually be probably 50. Seems like a more round number. But what happens is it will keep track of how many times it's saying it's getting rejected by whenever, and if it's too many above a threshold that's configurable, then it will give up and the test fails. So what you would want to do is not use whenever. So I can show a better way to do. Another way you might do this is, which I was going to show you anyway. Let's see if we can find this one. So I could make another generator. Like if I really only want 0 and 1, then I could make a generator that takes the Boolean generator and turns it into 0s or 1s. For example, I'll actually do that first. So if it's 0, 1, I might say val 0 zoogen 0 or 1. That's cool. Zoogen equals, and I'll say for x.
1 second, Bill. There's a comment.
Yes.
Yeah. So maybe the bad example would be to generate from 0 to 1.
So
in double.
Yes.
Yeah, from 0 to 1 in doubles. Okay.
Sure. We actually have one that does that. So let's make a property. Let's see. That would actually be true. X plus 1 should be greater than x. So I can actually do that. Whenever, let's make these doubles. And we'll say whenever x is greater than or equal to 0.0 and x is less than or equal to 1.0. So this should also blow up with an exhaustion error, I would think. Oh, actually, it didn't. So the funny thing about 0 and 1 is 25% of double values are actually between 0 and 1. So it's there. I got it to fail, and that was okay. That time it did run out. It did have too many discarded ones, but it didn't actually most of the time. So you got another flaky test. But there's one thing I could do is there is one called non-zero doubles. So I could either say that, or it's actually one called non-zero double values, for example. That should probably just solve it, because that only generates non-zero double values, and because of that, you could even get rid of that whenever. But what I'd have to do normally is write a new, whoops, I'll call it ZTO, val ZTO 021 gen equals, let's see, how would I do that? I would say, thing is, I don't know how, given any old double, how would I get it between 0 and 1? But that's what you'd want to do, is start with one of them, and then make it smaller than 1. Yeah, can't think of how to do the math to get any double down to between 0 and 1. Can anybody think of that? Yeah, I can show you the other example with ints, because I actually have that queued up here, and then we can go back to the double one. So this guy was int accept max value. So going back to the other one where it was, let's make this back to int, and I was having a whenever clause, x does not equal int.max value. That guy. What I could do is I could make a new generator of ints called ints accept max value, and it takes in any old int, and then it just changes one of them. Right? If I just care about, oh yeah, that's how I could do it for doubles. That's kind of a stupid way, but I could do that. Just change it to 0 or something if it's greater or less than. But anyway, what I did in this case is I just got, instead of like excluding it out, I changed it to 42, which is everyone's favorite number. And there's no need for an equal sign there. So now I don't actually, I can say for all ints accept max value. It will just never produce this. So even if I get rid of this, it won't. That should work. Let's try that. But that's basically the answer to your question of like, what do you do to have, your whenever clauses should just be for like a small subset of the possible generated values. That's when it makes sense. If it's like half of them, then you want to make a number generator that only produces those half. Another example was when I think I got rid of, I had shown you a demo of just getting rid of negative numbers by changing them to .apps, absolute value of the negative number. So that's an example of, half, if you want to get rid of just positive ones, or just get rid of all the negative ones, which is like half the range, then you want to actually make another generator. So are there any other questions?
Any other questions so far?
Yeah.
Doesn't look like it.
Okay. All right, let's move on. Oh, and show your randomizer. Okay. So I showed you that. Basically, what's going on when you see this code where it just says, the dark code, is that there's an implicit generator of events being passed in as an extra, hidden parameter. So it is based off the type of this function. So this, for all takes a function, and the type of the parameter or parameters, it can be up to 6 parameters. This one's an int, so I'm going to have a generator of ints. It's going to look for an implicit generator of ints, and it's going to find one which has the name int, so it just adds this to it. If you ask for doubles, then it's going to, look for an implicit generator of double. So that's actually how it works. And the idea is that you don't. Well, one thing that doing property-based testing is supposed to help you do is raise the level of abstraction of your tests. You're actually thinking about like, what is a. Really, you're thinking about what is a statement of logic that describes the specification of the behavior of my function that I'm testing. So that's kind of like a higher level than, okay, what happens if I pass in 42? But it also means you don't have to think up actual examples of doubles to try out. And sometimes people will forget edge conditions, so these things will also try edge conditions. Well, ScalaTest and ScalaCheck will try edge conditions to make sure that, you know, it works at the edges of your type. Okay, so let's do a couple of these more demos here. Oh, whoops, hang on a second. I'm not in. There we go. Okay, so here I have this one. It actually failed on maxint. And what you can do in Scala test syntax, either with, basically Scala test has integration with ScalaCheck. So most of what I'm showing you works for either one of these. That's what I'm looking for. So I'm going to make an int accept max values right here. So if I make this thing and I just turn max value into min value. So basically, what just to make sure you understand this, this says this is a generator of int, and I say for an int that's generated by that guy, I just compute a j, which is if that int happened to be equal to max value, I'm going to actually, my j will be min value. Otherwise, my j is going to be whatever was generated, and then I yield j. So I get a new generator of ints. The type of this is generator of int. It says so right here, and it's going to produce everything except int.max value. And so then I can actually put it there, and I think I showed you that already. If you want to, you can actually specify a oops, I have a typo here. Ints except max value, all ints except max value. Here we go. Okay, so if you want to, you can actually specify generators here. So if you have a function here that takes 2 parameters, you can put 2 generators here, for example. And then if you want to actually name the thing, so if you go back to my original failure up here, it just says occurred when past generated value max int right here. If I use this thing where I actually give it a name for all x, for all ints x, I kind of say it that way. Oops, it succeeded. I'll try it again. It's a flickering one, remember. Well, you should fail. Try int.max value. Come on. There we go. Now it says, you know, it says the name here. So that's another thing you can put. And you can do that with ScalaCheck also. And then you can actually do both of them. So I can say here that, so for all ints x, so this is naming the generator. That's the name of the default generator of ints in the ScalaTest one, and that's the name of the parameter. So when it fails, I get x equals. So okay, so that's essentially what you can do in both ScalaCheck and ScalaTest. And is there any questions about that? I'll come look back at you guys. Okay, no. Anybody?
There is
Yes.
one.
Yes.
One question. You're saying that this is new version. What version of Scala does it support? Does it support 3.3.11?
That's a good question. You can mute. Better answer. Thank you. The question was, what versions of Scala does it support? So the current version out is 3.0.5. That supports 2.10, 2.11, 2.12. And 3.1, we did decide to drop support for 2.10. And we decided to drop support for JDK 6 for 2.11. So 2.11 will be supported, but only on JDK 8. So right now, 2.10 to 2.11 are built with JDK 6. And then we have it also runs on Scala.js. We have a Scala native version that Scala native just is kind of not really usable yet. I mean, Scala.js support is actually used. And then we are just doing Dotty support now. So we're trying to get this running on Dotty 3.1. I just merged a pull request, which had a lot of it working. There's some of the macros aren't working yet. Okay, any other questions before I move on?
I don't want to hijack the conversation, but if we have a little bit of time towards the end of it, if we still have time, maybe if you could show us how DOTI support looks like it's in
Sure.
Alien or it's still Scala, what is it?
Okay, sure. Yeah, happy to. Remind me if I forget. Okay, so edge cases. I kind of mentioned edge cases. So ScalaCheck favors edge cases, and I want to show you how they do it. And so it's kind of entertaining. So this is one of the things that I didn't like. This was, by the way, ScalaCheck was inspired by Haskell's Quick Check. It was originally kind of a port, and then of course it evolved. That was, I don't know, 10 years ago or 8 years ago or something, a long time ago. So it's evolved in its own direction since then. But Quick Check did this the same way, the way they favor edge conditions. So I'm grabbing my arbitrary here, which contains the generator of int I want. So I have to say dot arbitrary to get it. So now I have a gen event. I can make samples. For example, hey, I got some 0, and I'm going to show you, like, see, that's like the second time I got the same thing back, right? Because it's an edge case, so it actually does it more often, and I got a 1. That's max int. That's max int again. There's a 0 again. Oh my god. Okay, that's like a random number. Okay, that's not anything. So what I'm going to do is I'm going to I'll show you what this is first. Let me just clear it. I'll show it to you first. So list.fill will create a new list. It's a constructor. I mean, it's a factory method. It'll create a list of length 1,000, and it fills each element by calling this guy, which has a side effect. Gen.sample gives me a new number each time, and then that's in a sum, right? And I have faith in the int generator that it will always be a sum, so I just say .get. So that's why I got all these numbers. So this is a list of length 1,000, and then what I'm going to do is group by, I don't know what to actually get that paragraph in it. There we go. So what this one will do is it makes a map from the int value to a list of itself. So what you can see, for example, here is that this number showed up once. So it's in a list by itself here, and it's mapped to itself. This number also showed up once. But the 0, which is an edge condition, showed up a whole bunch of times here. You can see it's mapped to all of its appearances, and it's a way to make group by is a great way to make a little what are those called? Anyway, a mapping, we'll call it that. And then if I go to the next one, what I'm going to do is filter out the ones that just have one element. So I'm going to say keep the ones. Filter means kind of retain. Keep the ones where the length is not equal to 1. So now I've got 0 in there, which is an edge conditions. I've got min int, which is an edge condition, right? But if I just show you what the keys are, there's just 5 of them, which are the edge conditions for int. So it's 0, 1, -1, min int, and max int. Okay, so now what I'm going to do is figure out the lengths. So what you can see is there's 89 zeros, there's 119 min-ints, there's 77 ones, there's 78 max ints, and there's 100 -1s. So let's see, add that up. If I just compute the sum of those values, I get 463. So you know what? It's like every time I do it in front of people, it's below 500. But sometimes it's above 500. Sometimes it's below 500. If there's people watching, it's below. So let's do another one just because, well, no, that's fine. We'll use 463. So 463, essentially, there's 460 repetitions of 5 edge conditions. So if you subtract 5 from that, I would get 458. Yeah, 458. 8 out of 1,000 times it was doing repeating the same test, essentially, test data. So that's how they do it. And what ScalaTest does differently is it does them first. So first we basically, there's this notion of edges, and we just try some edges for that type t, and then we spend the rest of the time trying evenly distributed t values. So we do the edges first, and then we just don't worry about edges after that. Okay, so here's an example of edges. So you can just ask a generator, this is the generator of ints, for edges, and it says, well, 0, -1, min int, 1, and max int are our edges for int. If I do doubles, then I get a whole bunch of them. One thing that's missing here is not a number, which I plan to add. Next time we go to questions, I'll ask you if you think that's a good idea or not. But here's minus infinity, plus infinity. There's like, this is the greatest magnitude negative number. This is the greatest magnitude positive number. Here's 1.0, negative 1.0. This is the smallest magnitude. It's like the closest to 0, but not 0. Negative and positive number, and then there is a minus 0, and there's, you know, non-minus 0. So so that's the idea. And then what you can do is, if I'm going to do a for all here, and I'm just going to print out what's passed in, so you can see what's passed in, and then I'll say succeed. So it'll never fail, but you'll see what gets passed in. So what we do by default is produce 20%. Well, we produce 20% edge cases if that can be filled. So here I got min-int and max-int, and the next time I run it, I got min-int and max-int again. This time I got -1 and max-int, -1 and 1, right? So essentially we'll do 20% edges, and the rest of it is just randomly distributed ints. Okay, so then if you, I say min successful 100, and the other thing that I did in ScalaTest a couple years ago, Haskell's quick check tried this 100 times by default. You can always configure it, but it was 100 by default, so most people left it at 100. It seems like a nice round number. And then ScalaCheck did that, and most people left it there. And so I did that in ScalaTest. I just left it at 100. And then what would happen in these property-based tests is you'd write the test, and you might find a bug or two. Rarely, actually, it's not that often. But then once you fix that bug, this would succeed for like decades, or not decades. Decades didn't go by, but years and years. You'd be running the same property-based tests over and over again, and they always succeed, but you run it 100 times. And it just felt like it was wasting time and electricity. And so I changed it to 10. That's why it's 10. But if I actually do it this way, and I say min successful 100, you can say, this is like, you can put configuration parameters right here in line. Now 20% is 20, but I only have 5 edge cases. So once we run out of edges, we just start generating random numbers. So here I didn't like repeat up until I got to 20%. I just said, well, I'm out. I'm going to do all the edges, then I'll just do randomly distributed things. But if I were to actually do tuples, so let me show you this one here. If I were to do tuples, so what this one does, I'm not sure you can actually see that. Let me move that up. Okay, is basically I'm saying for all tuples of ints, right? And it's going to give me it's going to generate tuples of ints up to 100. And so you will actually now get 20 because there's 20 combinations of them, right? So here's -1 combined with -1, 0 combined with 0, 1 combined with 1, right? And so what we're trying to do is not repeat, but we'll fill it up 20%, get that done, because that's actually, I think, the most likely place to find a bug is edge conditions. Then we just try it all over the place, right? So that's one thing we're trying to do differently. And another example is if I just make something called endpoints, I can make an endpoint generator like this. I could say for from in ints, for to in ints, give me an endpoints from to. That, and my generator, now I've got a generator of endpoints. So that's how you normally make them. And so then I can just, if you see this, it's going to be the same kind of thing as tuple 2s. Oh, I didn't say max. Yeah, see, it's the same thing. So I got 20% in this case. So anyway, that's that. Let me come back over and see if you guys have a question. And the one I do want to ask something in specific, which is, would you expect not a number to be coming out of the double and float generators? Would you want to try that in your tests and have that thrust in your face, saying, "Oh, you have to think about not a number or not a number"? Anybody have an opinion?
Would you like Bill to return on? To repeat the question, maybe, or the question? So I'm not sure. So let me to reiterate it so I understand, Bill. The question was if I would expect from my generator of numbers sometimes return me non-number as an edge case?
For double and float.
For double. Okay.
Yeah, because it is a valid value. And it's just most of the time people ignore it. And I think it is an edge condition, but it's not currently in our edges. But I think we should add it. If somebody had an opinion. But
I feel like I would add it because it is a condition, but maybe make a second one that doesn't have not a number and positive and negative infinity. I feel like those ones are often ones you would filter out.
Yep. Okay. We did that. I'll show you that. Okay, that's good. So let's see what else we got here. So I'll show you that when I get to this one. So in a couple demos away, I'll show you the way you get something without not a number. So another one is this notion of shrinking. Like let's see if I can do a test. I'll just do one off for all s:\string. Well, let's just say fail. What does succeed? What's the opposite of succeed? Do I have a well, I'll just say fail. Oops. That could work. That'll blow up. Oh, that completely backfired. I was going to try to show you what like a huge number you would get. You know what I'll do is I'll print them. That'll be prettier anyway. For all, I'll say print line s. Succeed. That's better. So you'll see them. I'll just show you what's the kind of strings that get generated out of these like crazy strings. So what you'll get is these test failures that have these wild numbers and values and things in there. And I like this alarm clock. But so what's shrinking, the idea of shrinking is, well maybe, you know, if you have this a test that's testing lists and it comes out with a list of length 10,000 failed the test, can you find a shorter list, a smaller list? So you try to shrink it. So once a test fails, once you've found some values, you know, that when you pass it into the function, it causes it to blow up. Shrinking is a phase where you're trying to see if you can get a smaller, prettier value to get the test to fail. It's kind of like when someone finds a bug in the Scala compiler, they ask you can you make it a smaller example, right? So that's what this is trying to do. So what ScalaCheck has is essentially this, whoops, well, 109, that's funny, 100. Essentially what it'll do is, like, let's say 100 is an int that caused your property to fail. It'll cut it in half and try that, and then, you know, the negative version of that, then cut that in half. It keeps trying to make it smaller and smaller and smaller as you go down. And then when you hit the end, if none of those caused the test to fail, they just show you 100, the one that causes the test to fail originally. But if it turns out that -6 causes it to fail, then it will show you that because that's smaller, essentially. And so what I'm going to show you is that the way ScalaCheck does that is there's a shrinker. It's the same way QuickCheck did it. The shrinker is separate from the generator. So I'm going to give you a generator. So here's the int generator. That's the same one we were using before. Let me just get rid of all that stuff so you can. So that's that. And then I'm going to make a non-zero int generator out of that. So we did this before. Here, I just said if it's 0, I'm going to change it to 1. Otherwise, I give back the int that was generated by my default generator for ints in ScalaCheck. So now I've got a new generator that knows how to generate. That will never generate a 0. So to make that the one that's used, I can actually put it inside an implicit arbitrary. So now that I've wrapped it in an arbitrary, and I made it implicit right here, this will be found when I try my for all. And I'm just going to actually use ScalaCheck directly though. So I can make a property like this. And what this says is first of all, I divided by I should be 1. And what's important is that I don't get a 0 passed in here, because if you pass in a 0, you're going to get a divide by 0 arithmetic exception. But this will fail because anytime you pass something greater than 1,000, it's only going to succeed if it's you know, not a 0 and it's less than 1,000. So I did get rid of things that are equal to 0 here, but I didn't get rid of big things. So it should actually fail, but look at how it failed. I mean, I have to do it more than once. Yeah, so I already got my divide by 0 error. So what happens is even though I am using a generator that won't produce zeros, the shrinker is picked up separately, and it doesn't know not to pass a 0 in. Remember these, the 0 is the last thing it tries. So it blew up during shrinking. And that was because when I, compose a new generator, we don't compose a new shrinker. People usually don't think of it. So what we try to do differently here is the shrinker is part of the generator. And when you compose a new generator, it will actually adjust the shrinker to match. So the way that looks, so I'm going to do the same kind of thing in ScalaTest's version so now I've got the same generator, but I made it implicit directly. We don't have an arbitrary. And now I can just do the same for all. And it failed, but it didn't blow up with an arithmetic exception. And what you can do is if you look at this guy, like I can just show you inst.shrink 100 R&D. Well, this gives you an iterator. Hang on a second. Val it comma underscore. So here's what the shrinks are for ints, all ints. If the thing that fails is 100, and so one other thing we do differently is we go in the other direction. We start small and get larger, and as soon as we find one, like let's say -6 or -3 causes it to fail, we're done. We don't have to go any farther. So it does include 0, of course, but if you look at the other guy, the one that we composed, we made a new one. I'm gonna have to do the same thing here. I'll just change it to this here. Okay, now we're using the new one. I'll say it.toList, and you'll see the 1 is actually replaced by 1, just like it is in the generator. So it doesn't. That's why it doesn't blow up. So that's another difference. Is we're trying to integrate shrinking and generating so that you don't have that problem. Because people make new generators all the time, and they don't make new shrinkers almost ever. Shrinking is just it's just for user friendliness, and it's really not that important. I think it's definitely not. It's better to just show the original 100 than it is to have to divide by 0 error. Okay, so let me stop before I go on to the next thing and see if anybody has a question. Anybody have a question about shrinking?
No questions on shrinking.
Okay.
You're right. No, people do not do shrinking, I guess.
Yeah, it's it's just I don't think it actually works that often that you can find something smaller that causes the property to fail. So, but it was in quick check, and so it was in ScalaCheck, and so it was in this. We carried the tradition forward. So what one of the comments you made was a type that doesn't have not a number, and so we have a bunch of any-vals in ScalaTest. Scalactic. Scalactic is a sister library to ScalaTest, where it includes things you could use in your production code. Things that were in ScalaTest that people wanted something like that in their production code. So we have a bunch of these types, and we have integrated those with the generator. So I can kind of go over here to, no, not there, here. So this is like any-vals, the any-vals package. If I click on the any-vals package, you can see there's a bunch of them. So finite double, it will not give you infinities, or it won't give you not a number. So if you, like a lot of times you're going to want to do your test for all finite doubles, essentially. And finite float's the same thing. But we have like negative finite double, negative or 0 double, a non-empty vector, non-zero long, positive finite float. There's all these things that I'm going to show you posint for a demo, but import any-vals. This is a Scalactic any-vals. So if I say posint 1, that's positive. Let's say 42. If I say -42, I get a compiler error, right? So this is the apply method. This is .apply. This gets rewritten to .apply, and the apply method. This apply method is implemented with a macro that will look at compile time, and if this is a literal, it can tell if it's valid or not, right? So that's nice. But if you said val x equals 42 and val y equals -42, it actually can't tell at compile time. If I say posint x, so I get another compiler error that says, I can only, it has to be invoked on a literal, right? So we suggest you use posint.from, and what posint.from is a different factory method that gives you back an option. So if I give you something that at runtime turns out to be valid, then you get it in a sum. Otherwise, you get it in a none. And if you have nearby evidence, like I say val z equals 100, I can see right there that it's valid. I can say posint.ensuring valid, and this is an assertion, essentially, and then it changes the type. So I called this ensuring because I felt this was a good kind of assertion to put all over your code, is where you have nearby evidence that something will always work. You say, well, I assert that right here, that this is valid. And then that assertion changes the type. So z starts out as type int, and now we have type, well, res44 is type posint. So I've taken my assertion and moved it into the type. And now you can pass it around and it knows it's a posint. And then if you, so let's call that A, I guess. Or what's it comes after Z? I should have started early. W equals res44. So that's my posint 100. So if you know, I need to pass in an int, it will just widen. You know, there's an implicit conversion from posint to int because that's always a safe widening conversion. Every posint will fit in an int. There's one to posint, positive or zero int. If you have one of those, you know, posint is a positive or zero int. If you wanted to, if something needs a negative int though, this will not work, right? Because that doesn't fit. And then you can even, like, if something takes a, like normally if I say x, is x an int? So if I say x and widen that to posint, again, I can't prove, I get a compiler error because I can't prove a compile time that this is valid. But if it's 42, or, you know, let's use a different number, 88, because of compile time, I can actually look. The thing that the implicit conversion is the apply method. You know, it takes an int and gives you back a posint. So it will actually widen, narrow the type if it's a literal. So that's what anyvals does. So they're pretty useful, I think, for expressing constraints in your production code anyway. And then what we did in, I'm going to show you ScalaTest, in our support for properties, all of our generators that we provide, let me get down, sorry. We're trying to work on the documentation. Generators for, common generators are based on these anyval types. So there's all, you know, the standard ones, byte, short, double, but here's generator finite double, and they are that type, finite float, neg finite double. So, you know, pretty much whatever people would most of the time want is what we're trying to provide, both in anyvals that you could use in your production code if you wanted to. But for sure, I think they're pretty useful in your tests. So what I could do over here, if I went back to this guy, ints except, well, I don't have one for that. I have to make my own. But like the one where it was, you know, the square root could actually take, the square root method could take a posy double. That would be element OP, that's down here. Positive or zero double, this one. So this, like, you could say for all pos, if your float method takes, I'm sorry, your square root method actually takes this type, then you wouldn't need to require anymore. And in your tests, then you just say for all posy doubles, you can, you know, express your property. And so that's anyval. So I'll make this break for questions. See if anybody needs it. Does anybody have a question about anyvals? Anyvals? Yes.
Yes, there is.
Yes.
So maybe talking about performance over
Oh, can you repeat that?
Sure. Performance. What would be the performance overhead over using the native types?
Okay, that's a great question. What, if you can mute me? What? That's really a question about anyvals themselves. These are called anyvals because they extend to anyval, you know, in Scala. And anyvals in Scala are not as nice as you'd want them to be. They may box. So the reason they may box is you can have them extend interfaces or traits that are called universal traits and that are all pure abstract. They're like Java interfaces. So they're more object-oriented, but then that means that if you put like anyvals in a list, they box. But of course, if you put ints in a list, they box also. But if you put anyvals like pos int in an array of, it won't go in as an array of int, it'll go in as an array of any Java-lang objects. So they're a little bit unsatisfying that way. And in Dotty, there's a new feature called opaque types, which gets rid of that. So in the future, we'd probably change these to opaque types instead of any-vals, so that it would never box, and it would be exactly the same performance as a primitive type. So it's really, the question you asked is a good question. It's really not about our use of them. It's really about Scala's feature, any-vals, because we're just using that feature. So any other questions? Okay. Go to the next guy. All right, another thing that was fixed in ScalaCheck since we started this project was ScalaCheck used to only generate constant functions. So what this is say for all functions from int to long. What does this say? List 1 to 3 map f. That'll never work, right? If I take whatever that function is and I pass it to map on a list of length 3, the resulting list has to have size 3, not 4. So of course I got a failure, but in the to string of that thing, it looks like this. This is actually the function that was passed in, and one of the things I wanted to make it possible is I can just say val f equals, and you can get rid of that ugly extra space. You can just copy and paste it and run it. So f of 42 is this, f of 43 is something else, right? So what it does have here is just a random int that the next time I run this, there'll be a different, like right now, if I pass 42 in again, I'm going to get the exact same thing. But the next time I run the test, no, not that, the test itself, this guy, I'll get a different, see this number is different? So now when I call, pass 42 to this, I'll call that G. It'll be different. So f of 42 is, well, 52, so that's fine. F of 42 is a different number. So each time you'd be getting different tests. So that's another thing that in ScalaCheck, there's something called cogen, which is, again, it's a kind of a category theory way of doing it. And what we did is we just used the hash code because there is one, and we were able to use hash code on whatever's passed in. No matter what's passed in, I can get a hash code for it, and that's how I generate a result. But anyway, so that's that one. And then async properties is something that people have asked for a lot. So let me show you that one. Right here, this is a method called addSoon that takes 0 to many ints and returns a future int, which is the sum. So inside a future, I'm going to print out, by the way, this is what was passed into me. Then I'm going to sleep 1,000 milliseconds, so a second. And then I'm just going to compute the sum. So what this test does is it says, let me move this over a little bit here. I call the method with 1 and 2, and I get back a future int. I call it future sum. So what Scala's async styles, and this is called async fun suite, do is the type of the test body that you pass in, the type of this thing needs to be a future assertion. So if you are working in future land in your APIs, and a lot of times people do that in Scala, then instead of blocking and when that future completes doing an assertion, you can just map that future, the final future you have, to an assertion and pass that back to ScalaTest. And what ScalaTest will do is register interest with that future to be notified when it completes, and it just puts it on a shelf. And then once it gets that notification that that future is completed, it looks at the result of that future, which is a future assertion, and it says, well, either the test succeeded or it failed, and it's going to it reports that to the reporter, so it shows up in the test report. So that's what I'm doing here is I'm taking the future sum and I map it, and I say, okay, the sum's coming in. I'm just going to assert that it's equal to 3, which should be true, unless I have a failure. No, that should actually work. So yeah. So let's just run that here. Test only star, what's this called? Async something. async property spec. Let's run it. It should succeed. Okay. And okay, so, and you can see what got passed in is this wrapped array 1, 2. And that's an example of like the traditional way of doing testing, not property-based testing, is you pick some numbers, right? So I picked 1 and 2. Okay, I tested my thing, I'm done. So what has been requested for a long time, and the people, you can't do this with ScalaCheck. We couldn't do it with ScalaCheck because we'd have to do surgery with ScalaCheck, is that I can do a for all based test, and it picks a list of events that I'm going to pass in. And so here I'm going to say for all lists event, when I pass that list of events in as var args to add soon and get a future sum back, and then I will, you know, the sum that comes back should be the sum of the lists in that, the ints in that list. So the result, this is a future assertion. So that's the end of my for all. And so what this will do, it has to actually do this for all in future space. So let's try running that guy. And it why did it fail? Oh, because it didn't come out. I have a duplicate test name. ScalaTest doesn't let you have duplicate test names. I commented out the old test and I put in the new one. Hello. There we go. So you can see it did try a lot more interesting lists. You know, it tried an empty list. It tried lists of various lengths and with various different ints in it. And that's the way that works. I can switch back to you guys. Is it can't iterate in the usual way. It can't just like try it once at a time. It has to chain futures together with flat map. So it just, you get this long chain of, like if we're going to try it 10 times, there's a chain of 10 futures. And then if one of them fails, we have to do a chain of futures to shrink it, that sort of thing. Because the property that we have in our hand generates a future, doesn't actually generate an int, it generates a future int. So are there any questions about async?
No, no questions.
No questions about async. All right. All right. What I can do, the last one I was going to show you just quickly, and then I'll show you the Dotty thing. Is if I can find it here. Is going back to I sort of felt like one of the other reasons I thought we should put that ScalaCheck should have a generator, ScalaTest, I mean, should have a generator, is that I think this is very fun. I'm going to go back to this slide right here, where I think this is very fundamental to what testing is about. And so I'm really specifying, you know, I can use a statement of logic to specify the behavior of a function that I'm writing. And